thank you. Thank you for coming in this cold and early morning. OK, so this is joint work with Puya Khatami. We're going to talk about Boolean functions. So these are functions taking n input bits and outputting 1 bit. We'll think of a Boolean domain as plus minus 1. And we can also think of a Boolean function as a coloring of the Boolean hypercube. So we have 2 to the n vertices. Each 2 vertices are adjacent if and only if they differ on exactly 1 coordinate. So each vertex has n neighbors. And we will simply color by the value of the function. If the value of the function is 1, we will color it blue. If it's minus 1, we will color it red. So what's the sensitivity? We look at some vertex, and we look at all its neighbors, and we count how many neighbors have different color. So in this particular example, for this vertex, the sensitivity is 2. For this vertex, the sensitivity is 0. And we will talk about the maximal sensitivity, taking the maximum of all vertices. OK, so in this case, it's 2. So the question is, can we construct interesting function with small maximal sensitivity? This is also called as the sensitivity conjecture. I'll frame it more formally in the next few slides. But if you think about it, it's a bit of a hard problem to solve, right? We want to color it in some ways that not almost, everywhere we want the color to be the same as almost all the neighbors. So it's kind of hard. We can obviously color everything blue or everything red, but this will be trivial. OK, so to define it formally, I need also to define degree. Degree of a Boolean function. I'm going to use the Fourier expansion of the function. So it is a widely used mathematical tool that you can, and a fact that you can represent a Boolean function as a multilinear polynomial. And there is a unique multilinear polynomial that agrees with the function on plus minus 1 to the n. This is the Fourier expansion. What it is, it's simply a sum of monomials times coefficients. So these are just real numbers. And it's unique, so you can actually calculate this coefficient from the function. And a useful fact is that the sum of squares of this coefficient equals 1. We will use it later to define some probability distribution. And what's the degree? It's simply the degree of this polynomial. OK, so what it is, it's simply the size of the maximal set such that the Fourier coefficient is non-zero, right? OK, so let's see an example. So this is the Boolean function that represents the majority on 3 bits. And when we write it as a polynomial, we can write it as this polynomial. And notice that if you will assign plus and minus 1s, let's assign 1s everywhere, then the value will be 1. Let's assign minus 1s, the value will be minus 1. And if more are 1, we'll get a 1. If more are minus 1, we'll get a minus 1. You can see here Parseval identity. Sum of squares equals 1. You can also see that the degree equals 3, because this is OK. So this is an example. So what the sensitivity conjecture asks us, informally it says that function with small maximal sensitivity must be simple. What do I mean by simple? So as Greg said, we can say simple as low-degree polynomials or small-depth decision trees. So I will define it with low-degree polynomials. So the Nissan-Szegedy conjecture says that the degree of any Boolean function is at most a polynomial in the maximal sensitivity. Okay, so this is wide open for more than 25 years now. And we are very far from resolving it. The best known upper bounds that we have are only exponential in terms of sensitivity. And the best separations that we know are quadratic. So we know that this C should be at least 2, but we don't know much more than that. Okay, so there's a huge gap. Upper bounds are exponential. Lower bounds are quadratic. We are far from resolving it. We will try to take intermediate steps toward this goal. OK, so a little bit of motivation. Why do we care about these complexity measures? They come naturally when we study query complexity, when we study decision trees. And we can study deterministic decision trees, or randomized decision trees, or quantum, or non-deterministic. And it's quite interesting that all of these measures for total Boolean functions are equivalent. They are the same up to polynomial factors. And it turns out, and this is, I think, very surprising, that it's also polynomially related to the degree as a polynomial, and to the approximate degree, and something called block sensitivities that Nissan defined. So actually, there's a much longer list of complexity measures. All of them are sort of equivalent. The sensitivity conjecture asks whether the sensitivity can join the party. whether the sensitivity is also polynomially related to all the rest. And this would be nice because it's a very simple measure to define. OK. So as Greg said, this line of work tries to prove consequences of the sensitivity conjecture. We can see it as an intermediate step. This is something that is implied by the conjecture. And sometimes it's non-trivial to prove even the consequence. So I want to mention two works. So the first was a work from ITCS 2 years ago that shows that actually low sensitivity function, you can think of like the maximum sensitivity as maybe log or polylog, they have a shallow depth formula. So you can think of it as something analog to NC1. And this in particular means that you have a succinct representation for such functions. And you can see it as an intermediate step. In the end, we'll want to get to decision trees, which are even simpler than formulas. And another previous work with Parikshit, Rocco, and Avi, we showed that low sensitivity function can be well approximated by low-degree polynomials. So the conjecture tells you that you can compute it exactly by low-degree polynomials. We only managed to show that you can approximate it. OK, so we get to the subject of this talk. We're trying to prove pseudorandom generators for low sensitivity function. So let's see one slide of what is pseudorandomness. So as Avi Vigdersson said, pseudorandomness is in the eye of the beholder. And in this case, the beholder is a low sensitivity function. So we want to construct a pseudorandom string. And we want it to look random for any low sensitivity function. OK, so I want a distribution over strings of length n. And I want any distinguisher, which is a low sensitivity function, to be not able to distinguish between the two cases. So it cannot distinguish between this case and this case. So the probability that it outputs 1 on this case is very similar to the probability that it outputs 1 on that case. So this is the definition. And what we want to do, we want to sample this distribution using a few random bits. So this is using a pseudorandom generator, which takes a short seed of S random bits, expanding it to a long sequence of n pseudorandom bits that look random to any low sensitivity function. So this is our goal. OK. So in this slide, we will try to construct, and in the rest of the talk, we'll try to construct pseudorandom generator for this class of function, sense S. These are all functions where the maximal sensitivity is at most S. You can think of S as maybe log n. This would be a good parameter to think of. So I think this is actually kind of nice because instead of looking at sensitivity as a complexity measure, we'll think of it as a complexity class, the class of all functions with sensitivity at most log n, let's say. Then we need to fool this class. OK, so what do we know from it? Let's assume the sensitivity conjecture. What do we know from that? We know that they can be represented by low-degree polynomials. Low-degree polynomials can be fooled by k-wise independence. So this is really easy if we assume the conjecture. OK, but we want to prove it unconditionally without assuming the conjecture. Maybe the conjecture is false. We don't know that. So the current bound that we know about between degree and sensitivity only gives us the 2 to the s-wise independent fools this class. If S is equals log n, this is trivial, right? This is just a uniform distribution. So we see that we don't get anything meaningful for S equals log n. We will try to take a step forward. OK, so if you think about it a bit, you realize that there must be a very easy solution because there is this connection between hardness and randomness. Right? Nissan and Vigdersson showed that any hard function implies a pseudorandom generator. Okay, so all we need to find is a hard function. And it turns out there is a hard function. Parity is very hard for low sensitivity function. It's exponentially hard. Okay, this was shown in this previous work. Okay, so just plug and play. The only problem is that there are a few assumptions in the proof. And in particular, one assumption that the class of distinguishers that we are dealing with is closed under projections, under identifying a few of the input bits. Let's say that the second bit equals the 10th bit. Okay, so this is something that is done in the construction. And actually, sensitivity might not be closed under this operation. In fact, it is the question whether or not it's closed under this operation is exactly equivalent to the sensitivity conjecture. So it seems that we are running, chasing our tails, and we seem to run in the same problem. OK, so perhaps it works, but we cannot prove it. So let's look at the second try. And this is a pseudorandom generator based on random restriction. So the basic idea is we want to fool this function f. Aita and Vigdusson showed that it is enough to fool f under a random restriction. And let's see why this works. So we apply some random restriction. OK, so this randomly picks location and fixes some of the location to randomly chosen constant. OK, so some of them are -1, some of them are 1, and the others remain alive variables. And what do we know, for example, from Hastad switching lemma? We know that under these random restrictions, the function becomes easier. OK, so let's say it becomes like a small depth decision tree. If it becomes easier, then we can fool it using, let's say, k-ways independent. So we can fool the restricted function using a pseudorandom string. OK, so we can fill in the alive variables using pseudorandom bits. And this means that if you think about it, we sample the constant uniformly at random, and we sample x2, x5, x6, x8, etc. pseudorandomly. So we got this partly random, partly pseudorandom string. And this fools the function f itself. OK, so this is indistinguishable from the totally uniform string. OK, so this looks kind of bad, because here we used a lot of random bits in order to sample this string, right? Maybe more than half. So the idea of Aita and Vigdusson is to recurse. Just look at these random bits and try to apply it again, to apply the same argument again. So we will flip some of them to pseudorandom. We will flip some of them to pseudorandom until everything is pseudorandom. And then we'll use an hybrid argument to say that, OK, each two of them are indistinguishable, so also the top one and the bottom one are indistinguishable, where we accumulate the error. OK, so this is the Aita-Vigdusson paradigm. It tells you that if you can fool a function under random restriction, where p is a parameter to stay alive, OK, p is what's the probability that a variable will stay alive under the restriction, and you used only t random bits, then by repeating it maybe 1 over p times log n many times, you fool the entire function. OK, so with this in mind, we just need to fool a function under random restriction. So what do we know from this previous result? We know that under truly random restriction, where each variable stays alive with probability p, the probability that the degree is bigger or equal than d is exponentially small in ps to the d. This is sort of similar to a switching lemma type statement. And if you pick the parameters right, you can see that by picking d to be roughly log n and p to be 1 over s, with high probability, you would get that the function has degree, let's say, at most log n under the random restriction. And then you can fool it using log n ways independent. Okay, so this would give us very good result, very good seed length. Unfortunately, this result holds under truly random restriction. And what we want to do is we want to pick the location, which variables stay alive and which variables are restricted. We want to pick it pseudo-randomly. We cannot do it randomly. And unfortunately, we don't know how to de-randomize this argument. OK, so we couldn't do it efficiently. So we need to come up with new techniques. So let's see our main theorem. We show that this approach works, but with a little bit less good parameters. We show that it works with seed length, which is exponential in square root s. OK? So for example, if you think of s as log n, it's a sub-polynomial. It's 2 to the square root log n. But it becomes trivial when s is, let's say, bigger than log squared. So for some interval in the middle, we get some interesting results. OK. So a little bit about the techniques. We're analyzing moments of two distributions. So we take the Boolean function, and we'll associate with it two distributions. One we'll call the sensitivity distribution, sample a point uniformly at random, and output the sensitivity of this point. The second is the Fourier distribution. sample a set according to the Fourier coefficient square of this set, and recall that this is a probability distribution by Parseval, and output the size of this set. So these two distributions were studied in the past, and for example, well-used fact is that the expectation of these two distributions are the same. So the expectation of this one is simply the average sensitivity. The expectation of this one is what's called total influence, and they are equal. OK, so we will define sort of higher moments of these random variables. The expectation of x choose k. We could have picked x to the k, but somehow this is more natural and easier to handle. And the expectation of y choose k. So we'll call this the sensitivity moments, and we'll call this the influence moments. And in this previous work, we showed that the influence moment is at most the maximal sensitivity raised to the power k. In the follow-up work, we showed the connection between the influence moment and the sensitivity moments. But I will use only this result. OK, so what's nice about these influence moments is that they behave very nicely under pseudorandom restriction. When we pick every coordinate with probability p, and we do it using a k-wise independent, then these moments are multiplied by p to the k, exactly on expectation. So there's no constant, nothing. It's exactly p to the k. So let's say that we started with a function with sensitivity s. So its moments are at most s to the k and order s to the k. And then we apply the pseudorandom restriction, and these things are multiplied by p to the k. OK, so we are doing everything with k-wise independent. Think of k as pretty small. OK, so we managed to get these numbers to be very, very small. So these moments are actually much smaller than 1. So we pick the right parameter so that these things will be exponentially small in s, actually. OK, and so to pick the parameters, we pick k to be square root s and p to be 2 to the minus square root s. And this is where the 2 to the square root s will come from. OK, so this is what happens after the random restriction. And now we want to show, OK, now we can fool this function. So this is the main structural result. We show that if you have a Boolean function, its maximal sensitivity is at most s. We know that this holds for the restricted function because sensitivity cannot go up if you take subcubes, if you take a random restriction. The sensitivity moment is at most exponentially small in s, and the influence moment is at most exponentially small in s. Then the function is exactly a 2 to the order k junta. Okay, and this is a structural result that may be interesting on its own right. And it holds for any k, and we prove it. We use it with k, which is roughly square root s. And I want don't have a lot of time, so I just want to tell you maybe 2 sentences about this result. So we start with Friedgott result. Friedgott starts with an assumption on the influence and gets to the fact that you can approximate it using a junta. So if you just take this assumption C, and you take the Friedgott junta theorem, you would get that you can approximate G with error 2 to the minus order k by a junta with this many variables. Okay, so 2 to the square root s. We show that if you also assume A and B, then the error is actually 0. Okay, so this is the main new techniques. And we are using sort of isoparametric inequalities to prove it. Basically, the fact that a function with maximal sensitivity s cannot be too close to 0. If they are too close to 0, they are the 0 function. OK, so that's all that I want to say about this thing. And once we are at 2 to the order square root s junta, you can fool it using 2 to the order square root y independent, and plugging it to the Itay-Wigderson framework, we are done. OK, so this is all that I want to tell you. Thank you very much. And I think that, sorry. So 2 things that are open. So obviously to improve the parameters. So currently we get 2 to the square root s. We can hope to get maybe polynomial in s. And I think that it's also interesting to see where the Itay-Wigderson PRG can be useful. And we also so it's useful for AC0 and branching programs. So it's very interesting pseudorandom generator. Thanks. Okay. Yes.
The question about whether poly-S-wise independence pools sensitivity S, how close is that to the full sensitivity?
It's a great question. It actually implies something interesting. So if you prove that any poly-S-wise independent fools this class of function, then you actually show that there exists sandwiching polynomials. So not exactly a polynomial that equals the function, but like a polynomial that upper bounds the functions, a polynomial that lower bounds the function with the right degrees, and that they are on average very close to one another. So I think it will be very interesting to show such a result because it will say something towards the conjecture, some structural result.